So last class, just how many protons, neutrons, and electrons are there? Isotopes are dealing with the nucleus. How many protons versus neutrons are there? Electrons are on the outside of the atom, and they play the biggest role in the behavior of atoms when it comes to how they bond and how they chemically react. And that's a good portion of what we're doing the rest of the entire school year. Bonding is what we're going to talk about in the next unit. That's going to get us through first semester. How they react or how they interact with mixing and things like that is what we talk about second semester primarily. So understanding electrons is important. But our understanding of electrons isn't probably where it needs to be because you, at this point in your life, haven't covered chemistry to the point where you really need to understand it. But now we do need to get into that. So again, what we're going to do is you have a guided note sheet. At times I'm going to tell you things that we need to fill in to help out with this. And then I'm going to go over things up on here. So you don't have to write down everything that's on here. You just want this packet and to kind of follow along. And when I indicate we need to go over something, let's go over it. As I just showed you with the Niels Bohr model of the atom, he thought that there are different energy levels that the electrons were in because of how he saw different colors given off by hydrogen with its one electron. The book kind of showed you a staircase or a ladder, rather, of these different steps. That energy level is somewhat true. We use that idea today because your observation holds true with what he saw as well. So what he said is the electrons always start closest to the nucleus and they build out as an atom gets larger. And that is also true today. The Bohr model of the atom is a very common representation of the atom. Now, as I noted at the bottom of the slide, it's not actually a fully accurate model of the atom. That's going to be the Schrodinger model we're going to go over in a little bit here. However, it is a useful model of the atom that sometimes we use. So what I want us to be able to practice is drawing a Bohr model. So the example given that we're going to do on your guided note sheet at the top here is going to be for calcium-41. So what I will do is I will go over to the Smart Notebook, and we have a nucleus. Inside that nucleus, we have protons and neutrons. How many protons does calcium-41 have? 20? And we look at the atomic number, we come up with 20. How many neutrons does calcium-41 have? 21. Remember, protons plus neutrons equals the mass. Now, when I look at your sheet, there are 4 rings shown. Again, typically, we give you a blank piece of paper, and you have to draw this entire thing out. Okay. Drawing the Bohr model for the atom requires us to look at our periodic table. So how about you get out your periodic table? In fact, we're going to be drawing on this periodic table at some point in the class today. So periodic table has columns and it has rows. We are going to focus on the rows that go across right now. How many elements are in the first row that goes across? 2. So hydrogen's the first, helium's the second, right? That means that first row across is like Bohr's first ring of electrons. And that there would be 1, 2 electrons in that first ring. And the periodic table is arranged the way it is for a reason. It's not a perfect rectangle or a perfect square. Today and next class in particular, we're going to learn about that arrangement. Second row across, how many elements are there? 8. 8 dots. Third row across, 8. Now, calcium is in the fourth row. That's why I have 4 shells to begin with. But it's not all the way at the end. It's the second element in there, correct? So I should only have 2 dots on my last one. This would be the Bohr model for calcium 41. The 41 comes from the mass that I indicate in the nucleus, 20 protons, 21 neutrons. And then, in my first shell, I have 2 electrons. In my second shell, I have 8 electrons. In my third shell, I have 8 electrons. In my fourth shell, I have 2 electrons. If I add 2 plus 8 plus 8 plus 2, that gets me 20. 20 protons balance out with 20 electrons. By the way, some people, when they do a Bohr model, they don't even show the dots. They show the rings, and they just write down the number of electrons in each ring. I'd accept either what I did in blue or what I did in red. Both are good answers. Hey, Jordan.
So was there 4 rings because calcium was on the 4?
Yes, exactly. So, if I go back to my PowerPoint now, we are actually going to label those energy levels on our periodic table. I want you to write on your periodic table that this first period across, the hydrogen helium, I want you to put a big number 1 right on that left-hand side of your periodic table. And I want you to number down each row to 7, where francium is. Energy levels from Bohr is something that we still recognize. However, it's only a piece of the puzzle. Don't do anything with those bottom 2 cutout rows right now. We're going to talk about those next class, because that's when things get a little weird. All right, so I've shown you the Bohr model, and we've gone over this idea of energy levels. That's what Bohr gave us, but that's only part of the picture. Do you have any questions yet? Okay, good, because right now this should be fairly straightforward. However, that rings around the nucleus is like planets around the sun, and that is not how electrons travel. Their travel is a lot more complicated than that. I really like the textbook showing that fan and how blurry it was. You don't know where the fan blade is at any moment. You just know it's in this blurry region. That's kind of like electrons. Now, there's someone called Werner Heisenberg who came up with something called the Heisenberg uncertainty principle that talks about we don't know the exact location or momentum of a particle at any moment. So Bohr's model of the atom of rings around the nucleus isn't quite right. We need to add on to that. And then Erwin Schrödinger is the one who, with some math, came up with this idea of orbitals. Not an orbit, like how Earth orbits around the sun, but an orbital, which is an electron cloud. A little bit more like that fan blade. It's a location where an electron is most likely to be located. So this is where things get a little different, because most people recognize Bohr models, simple rings around. But an atom is not that simple. So Schrödinger gave us this. So how do we represent this? Well, first off, there are 4 different orbitals. There's the S, the P, the D, and the F. So in other words, you did numbers 1 through 7 for energy level. We're going to use letters for the different orbitals. You'll notice on your guided note sheet, there's a picture on the right-hand side, sorry that the copy isn't as crisp as it could be, that says S and P orbitals. Those are the ones that we're going to talk about today. The D and the F are a little bit more complicated. But what you can see is I have a picture up on the smartboard right now. The S orbital is more of a spherical shape. Now that means an electron could be anywhere in that cloud. It doesn't mean that necessarily the electron is just going around the outside. It's buzzing around anywhere in here. The p orbital is split up into what we call 3 suborbitals. And it's a little bit more figure 8-ish, where this is going left to right, this is top to bottom, and the z-axis would be going towards you or away from you. Because again, atoms are 3-dimensional. And that's one of the drawbacks of a Bohr model, A Bohr model is a 2D representation of something that's 3D. I mean, if you ever look at a map of the world, Greenland's either ridiculously huge or ridiculously small because they're trying to show in 2 dimensions something that's 3-dimensional and just doesn't work well. Similar thing could be said about this because things get complicated. However, let's take a little time right now to label our periodic table and then go over this. These first 2 columns of the periodic table contain electrons that would be in the s orbital. Now, some people like to even highlight around those first 2 columns to really make that stand out. If you want to do that, feel free to grab something to do that with or just kind of pencil shade it in hard. I even have colored pencils in the back of the room if that helps out. But again, the first 2 columns down, all the way down to the radium francium, these 2 columns, electrons from there are in the s orbital. Helium on the far right-hand side technically is part of that as well. The p orbital is going to be the last 6 columns, boron through neon on down. So this block right here is the p orbital on the far right-hand side of your periodic table. So I would, again, maybe box this in, highlight if you want to, write a big P above that section. The d orbital, which we're not going to talk about today, but however, we might as well label our periodic table. The d orbital starts at scandium and goes to zinc. It's the middle of the periodic table where there's that dip. Finally, the f orbital, or the f block, that is the bottom 2 rows of the periodic table that seem separate from everything else. So hopefully we have numbers on the left-hand side and labels and again outlines or however you help to show S, P, D, and F orbitals. And this really is why the periodic table is the shape that it is. If they made it a perfect square or a rectangle, we wouldn't be able to break it up into these parts that we know these electrons are located in. So most people, why is it this weird shape? Well, there's a reason behind it. Because once you understand electrons, now you understand why it is the shape that it is. So we'll give you about 30 more seconds to kind of shade this in. Again, the one abnormality with this is notice how next to hydrogen there's a little blank space right there? Well, that's what helium would fill normally. So helium is part of the S. It's just on the far right-hand side. There's a reason it's on the far right-hand side that we will get into next week, dealing with what we call the families of the periodic table. Because the periodic table is arranged a certain way for a lot of reasons. Showing the number of electrons, showing the orbitals, showing elements that have similar properties to one another. And we've gone over the history of the atom a little bit. There's a history of the periodic table that we could have went over as well. And we started with the 4 original elements, you know, earth, fire, the water, wind. And then we could have gone into like the 12 or so elements that they first discovered, a lot of them that have those Latin names to them. So we could go more in depth than that at some point, but we kind of choose not to. Okay. I'm going back to this idea of orbitals and then what's referred to as suborbitals. And this is referenced on your note sheet next to where it has a picture of the S and P orbitals. This is the P orbital. If you combine these 3 pictures on my screen into one big clump, that's what the P orbital would look like. However, the P orbital is split into 3 what we call suborbitals. They're almost like 3 separate rooms that makes up this house for the electrons. It's important to note my second bullet point here. Each suborbital, so each of these separate rooms, can contain a maximum of 2 electrons in it. Electrons are negatively charged particles. if you have multiple negatively charged particles in the same area, they would repel each other. Recall that same charges repel. So in other words, I could have an electron buzzing around kind of in this lobe, this region of the room. I could have a second one on the other side. But where would a third fit? It can't fit in this room because now there'd be repulsion. And that balance between attraction between electrons and protons and then repulsion between the electrons on the outside is something that we will learn more about in this unit. For now, there is a table on your note sheet. It has a column that says orbital, S and P. It has a column that says number of suborbitals, and it has a column that says number of electrons when full. There are 3 separate suborbitals for the P. So why don't you put the number 3 for the suborbitals for the P. When you look at your note sheet on that right-hand side, how many pictures, how many suborbitals does it show for the S? 1. So let's put the number 1 next to the S. If 2 electrons maximum can fit into each suborbital, how many total electrons can fit into the S? 2. How many total electrons can fit into the P? 6. 3 rooms, 2 per, that gets you to your 6. I'll go back to our periodic table for a second. In that S orbital that we drew, there are 2 elements per row. 2 electrons is what can be fit in the S. In our P, on the far right-hand side, there's 1, 2, 3, 4, 5, 6 across. Because each time you gain an element with a proton, it also gains an electron to be neutral. It shows 6 there as well. And the arrangement of the periodic table is for a certain reason. We have you fill in that table. I don't know if it's a matter of memorization, because it's just recognizing what's going on through periodic table. Now, this leads us to how we are going to show electrons for things. And unfortunately, even though the board diagram looks nice and pretty, like a bullseye or like, you know, the sun with planets orbiting around it is what people have typically done, it's not the proper way to show electrons. I'm going to today show you 3 different ways to represent electrons, where they're located, the behavior of them, things of that nature. However, none of the ways I'm showing you after that Bohr model that we started class with, none of them are a picture of the atom. Because once Erwin Schrödinger got involved, he realized the atom is too complicated to actually draw out. You're trying to draw something 3D that has parts that are moving at almost the speed of light around it in a 2-dimensional still picture, you can't do it. So we are admitting defeat that we are not going to draw pretty little pictures of atoms in this class. But what we are going to do is focus on the electrons and how to represent them, because the electrons play such a major role in all of chemistry. Orbital notation is one of the 3 ways that we can show you this. Now I'm actually going to write out the orbital notation for something. That's what you have a space for on here. Okay, you don't have to worry necessarily about defining it. However, we're going to be using arrows to represent electrons. Not only do we need to know where electrons are located, but we also need to know the spin of them, and arrows represent that. In a minute here, I'm going to show you potassium and how that works. Before I do that, I am going to go over a couple other definitions that we will go back to in our note sheet in a little bit. One of them is called Pauli's exclusion principle, that states arrows represent the spin of an electron. 2 electrons in the same suborbital can't have the same spin. Let's say, for example, that over the holiday season you have family coming to visit. And you have so many family members coming to visit that there is not enough bedrooms in the house to have everyone have their own room. So now people have to start to double up. All right, Andrew, we're going with you on this one. What's your sister's name again? Jenna. So at the Wilson household, people have to start doubling up. and the parents make Andrew and Jenna double up in the same bed. That's awkward, right? Yes, it is. So, if you have to sleep next to them, or for example, I recently got a pop-up camper, and sometimes you have to put two people next to each other. The last thing Andrew wants when he wakes up in the morning is for Jenna's face to be right there. I mean, he'd be that close to kissing his sister, and you don't want to do that, right? Okay, good. I mean, again, maybe Jenna's a drooler too, and now maybe the drool is coming next. No, you don't want any of that happening. If you have to share that bed because the Wilson household is full of people, they alternate how they sleep. One sleeps this way, the other one sleeps the other way. That way, she can wake up next to your feet. That's not a problem. She's shorter than you, so you don't have to wake up next to her feet either. It's a win-win for you. And if she's going to drool, all she's going to do is drool a little bit on your feet. She's not, well, I know that's not great, but it's better than drool going into your mouth or something like that from your sister. Pauli's exclusion principle is when you put two electrons in the same room, they're not going the same way. Now that really deals more with repulsion, although at the same time, I bet in the Wilson household, it'd be a little bit of repulsion if they were both sleeping in the same bedroom, facing the same way. So they switch them around. Hund's rule is, hold on a second, let's not double up unless we actually have to. Hund's rule says when you have multiple suborbitals, one electron is going to go into each before they actually double up. So what I'm going to do, and again, this is a little weird early on for students, is I am going to draw the orbital notation for potassium. And this is what I want you to follow along with when it says example on your note sheet. Again, we are not trying to draw atoms. We're not doing Bohr models. We are admitting defeat to that. We are trying to show where electrons are located. So we're on the front page here, where there should be a blank for yours. Every element starts the same way. There's a nucleus, and then we build out. Niels Bohr was right with that. And when we start building out, we start in the first energy level, the number 1. Don't you have a number 1 written in the top left-hand corner of your periodic table? And what letter do you have written there? S. Because every element starts in the 1s orbital. I'm going to draw a line over the top. Sometimes you'll see textbooks with actual boxes. I'm going to draw an arrow up. That arrow up represents an electron. And if this was a neutral atom, ladies and gentlemen, I just drew the orbital notation for hydrogen. Because hydrogen has 1 electron when it's neutral. Remember the Bohr diagram? With what we're going over today in next class, you need to learn how to read your periodic table like a book, left to right. And if you're at hydrogen and you start to make your way right, what do you hit eventually? Helium, the second element on the periodic table. That second element has 2 protons, and when neutral, it has 2 electrons. So I need to add a second electron. I would show a down arrow. Again, the Wilsons do not sleep with their faces touching each other. That would be weird. Technically, again, these represent the spin of electrons, but sometimes that's a way to remember it. I mean, Andrew's not going to forget this now. Once you get to the end of a line, just like if you're reading a book, you start at the beginning of the next line. We filled the 1s because you can only fit 2 electrons in it. So now we move on to the 2s. The third element on the periodic table is lithium. Lithium with its third proton would need a third electron to be neutral. After lithium comes beryllium, which would be this. Every element builds out the same way. They start with the innermost electrons and they work to get bigger and bigger. More energy levels, more orbitals later on as well. Once we get to beryllium, we have to cross upon a little gap, and that gets us to boron. Now boron, we still have a 2 in front of it, but what letter do we have written in that boron area? P. There are 3 suborbitals in the 2p. I represent that with 3 separate rooms, or dashes in this case. My first electron, this would be the orbital notation for boron. Has 5 electrons shown. After boron on the periodic table comes carbon. Now, this is where, according to Hund's rule, I am not going to double them up right now. If there's an empty suborbital, it goes in there first. This would be the orbital notation for carbon. And by the way, if I asked you to stop at carbon, I would want you to draw that there are 3 suborbitals, even though there's nothing in this one. Because again, we are trying to demonstrate where things are within that atom. However, nitrogen would get us here. And now, each suborbital is filled with 1 electron. We do have to double up. And when we double up, we flip the spin. So oxygen, fluorine, and neon. I mean, there's times when we can do orbital notation for something at the very bottom of the periodic table. And if you can do that, you can do every element before because of how elements build up. What comes after 2p? Look at your periodic table again. You got to the end of one line. 3s. 3s only has 1 suborbital. You fit 2 electrons in it. That'll work for sodium and magnesium. Now, ladies and gentlemen, I'm starting to run out of space. So I'm going to continue down below. If you still have space on the right-hand side, feel free to continue writing there. So I'm not trying to say this is how you do it. This is more of, I ran out of space. After 3s should come 3p. And there are 3 suborbitals in the 3p. So right now, we should be where aluminum is on the periodic table. Arrow up for aluminum. Second arrow up for silicone. Third arrow up for phosphorus. And notice I'm just doing half arrows. I don't do full arrows. Just like I drop an E in mole. It's pretty common practice to do it this way. To still show it, but not waste any more time. That's sulfur, chlorine, argon. Which brings us to 4s. Potassium is the first element in the 4s. So its electron is the first one. And then we stop. This is the orbital notation for potassium. Early on, I get it that this seems weird. However, if you treat it like a pattern, if you treat it like just reading the periodic table, it's not that bad. But that's where some people are, again, still trying to draw circles around a nucleus. It's not that simple. Now, on your note sheet, it said rules for orbital notation. There's a big blank because we're going to have you fill in something right now. It says, arrows represent the spin of the electron. 2 electrons in the same suborbital can't have the same spin. If I go back to my slide here, that is Pauli's exclusion principle. So how about you fill in the blank there, Pauli's exclusion principle, on the bottom of your note-taking sheet. Notice how it shows an incorrect way to demonstrate that? I would like you then to fill in a blank of how could you correctly demonstrate Pauli's exclusion principle. This is actually a common thing that we've done on unit tests before, is where we'll give you an incorrect orbital notation. You have to explain why it's incorrect or make it right. Okay, so again, on the bottom of your first page, you filled in Pauli's exclusion principle. And then I showed you the incorrect way to show 2 electrons in the same suborbital. I would like you to do a demonstration of it being correct instead. When you get to the back side, the second rule was Hund's rule. Hund's rule states that each suborbital must have one electron before a second can fit in. So again, you can fill in the blank on the very top of that second page with Hund's rule. And then you see an incorrect way to end something. I want you to draw it out correct, where it says correct next to it. We go over this because whether you realize it or not, there is a lot of application to knowing where electrons are. Some of which we don't teach in Chem 1. Some we do. Some we teach in AP chemistry. Some we don't. Some of it you got to take college courses to do it. There's something called quantum numbers that describes electrons. I bet you saw the word quantum when you were reading about Schrodinger a little bit. Quantum numbers I could teach you if you knew orbital notation. It's really not that bad. I mean, one of them is either a +1/2 or a -1/2. That just depends on if your arrow's going up or if your arrow's going down. So there's different numbers to express what we just drew out. We're not going to get to that level in this course. However, we need to be able to practice that and know how to do that. That being said, there's two shorter ways to do what we just did. Because sometimes we don't need to know the spin of the electrons, for example. So we need to know also how to do what's called electron configuration. And what this says is we're still going to show what orbitals and energy levels we have, and we're not too worried about the spin of the electron. So I'm going to go back to my smart notebook here. And if you remember, this is what our orbital notation is. We're going to summarize it a little bit. So if I do the electron configuration for potassium, 1s2. That's how I start. The 2 is what we call a superscript. It's up higher. Energy level, orbital, how many electrons? After 1s2, 2s2. Because in the second energy level, in the s orbital, I have 2 electrons. After 2s2 comes 2p6. And you can look back at your previous page. You have 6 arrows above the 2p. That's what that superscript 2 is trying to, or 6 is trying to tell me. After 2p6 comes 3s2. After 3s2 comes 3p6, and I end in a 4s1. Electron configuration still shows energy levels, still shows orbitals, and with a superscript, it shows how many electrons. It just doesn't show arrows. Okay? Now, underneath that example on your sheet, it says shorthand electron configuration. There's another way we can do that that's even shorter than this. And what the shorthand electron configuration is trying to do is only show us the last shell. So, if we are trying to write this for potassium, that means these first 3 rows we know are full completely. So instead of writing out 1s2, 2s2, 2p6, 3s2, 3p6, there's got to be a shorter way that we can say all of those outside rows are full. And the way we do that is we go to the end of the line, to this column right here, which would end each shell. And we're just going to write down that previous element there. One of the things that you're going to learn in the coming weeks is this entire column of the periodic table has a special name. It's called noble gases. So sometimes the shorthand form that we're about to do is called the noble gas form, where you start off in brackets writing down the previous noble gas, the element that ended a line, because that is the same as writing all of this. 1s2, 2s2, 2p6, 3s2, 3p6. And then we just have to fill in the outermost shell, 4s1. So there are 3 ways that we need to show you how to represent electrons. Now, this is it for the weights. What we have to go over a little bit more the rest of today and tomorrow, or next class rather, is different examples that are a little bit trickier than others. Okay, here we go. On the very top of the third page of your packet, it has the question of what are ions? Here's our definition. An ion is an atom that gained or lost an electron or electrons. This gives it a charge. I've given you the term ions on the last few homeworks dealing with mole conversions. I want you to get comfortable with just that word. Now we're going to start to look at how the number of electrons are different for ions versus other things. Recall that when we did our work with subatomic particles, if you lose electrons, you're a positive ion. If you gain electrons, you're a negative ion. What I'm going to do to wrap up notes today is give you an example for both of these. Okay? So again, I'm going to go back to the Smart Notebook, and you see a space on your note sheet where it says electron configuration for calcium +2, and then for nitrogen -3. Let's go over both of those examples to wrap up class. By the way, it can be written as calcium +2 or calcium 2+. They basically mean the same thing for you guys. So you might see it written one way or the other. We are going to do not orbital with the up and down arrows, just electron configuration. So I'm going to first write it for calcium. Calcium is element number 20. I'll start with 1s2, because it always starts the same way and builds up. 2s2, 2p6, that would get me to neon, 3s2, 3p6, and I end in 4s2. If I was asking you to solve for calcium, neutral calcium, this would be correct. However, I'm asking you to solve for calcium with a +2 charge, which means it lost 2 electrons. And when you lose electrons, you lose the outermost ones. When you think of it, you're going to take off some clothes, you start by taking out the outermost layer. I can't take off my socks until I take off my shoes. Same thing here. We are going to lose the outermost. This would be the electron configuration for calcium +2, because it lost 2 electrons. It lost the 4s electrons. Last problem. N-3. Again, if we start by just looking where nitrogen is, nitrogen would be 1s2, 2s2, and 2p3. I don't know if you noticed this or not, but if you add up the superscripts, 2 here, 2 here, 3 here, 2 + 2 + 3 is 7. Just like nitrogen is element 7 when it's neutral. That shows the number of electrons. However, if it's nitrogen with a -3 charge, that means it gained 3 electrons. So instead of ending in 2p3, I need to end in 2p6. When doing ions, positive or negative, it is sometimes helpful just to figure out what the neutral element would be, and then either take away electrons if it's a positive ion, or add electrons if it's a negative ion.